I'm Will,
And I'm Meghana.
and we worked with the Atkin Lab.
The Atkin Lab's main focus is on material analysis at the molecular scale using the cutting-edge technology of scanning near-field optical microscopy, or SNOM for short. In this video, we will explain the way each of these technologies function and how they relate to each other.
SNOM is essentially the combination of laser spectroscopy and atomic force microscopy, and it was developed to increase the detail visible in nanometric imaging. Understanding how this works begins with a basic understanding of laser spectroscopy, which has traditionally been used to analyze molecular structures.
Laser spectroscopy works by using a laser of light with a certain wavelength to excite the electrons on the surface of a particular substance. When the electrons return to a lower energy state, we can then observe certain properties based on the light emitted.
However, the primary barrier in using laser spectroscopy is a property of nature called the diffraction limit. The diffraction limit is essentially a limit to the diameter of the light wave, which prevents experimenters from using a narrow enough beam of light relative to the size of the material. The diffraction limit is proportional to half the wavelength of light, making the area of space measured to about 50 to 100 nanometers given the shortest wavelength of light that is feasible to use. This is several times larger than the average molecule, which prevents accurate measurement of the majority of materials. For example, the diameter of adenosine triphosphate, or ATP, is a mere 0.14 nanometers, which is significantly smaller than what traditional laser spectroscopy can measure as a result of the diffraction limit on light.
Because of the diffraction limit, measurements are not as accurate. With a larger area of the substance being covered by one light wave, the data collected ends up being more of an average of the entire area rather than of individual particles, limiting our certainty of the properties we measure.
SNOM, the kind of microscope that the Atkin Lab works with, combines laser spectroscopy with another technology to surpass the diffraction limit. This other technology is called atomic force microscopy, or AFM.
AFM works by using a tiny metal tip to probe a substance and obtain data about the physical structure of the surface or the topography. This is shown in the animation, wherein the tip measures data about the substance underneath it by repeatedly approaching it. The quote-unquote near-field aspect of this shows most when the titanium tip approaches the substance very closely. Because electrons have the tendency to coagulate around a metal tip, there is a partially negative field occurring between the tip and the substance. In this negative field, there is some deflection of light experienced by the surface underneath the tip, which can reveal many properties about the surface.
By focusing a beam of light into a titanium tip, SNOM combines the fundamental principles of laser spectroscopy and atomic force microscopy to achieve a far greater resolution than previously used. When the light concentrates at the sharpest point of the tip, characteristic of AFM, its diameter is then reduced past the diffraction limit to as small as 10 nanometers, which overcomes the diffraction limit by a factor of 5. This defeats one of the greatest limitations to laser spectroscopy. Now we will do a walkthrough of the lab itself, so that we can see how these principles actually play out when doing experiments.
The Atkin Lab is primarily located on the first and second floors of Murray Venable Hall alongside other inorganic and physical chemistry labs. They operate their various laser setups on tables that rest on pneumatic pistons to ensure stability. The laser for the particular setup we analyzed operates in the infrared spectrum, which is only visible with thermal paper as seen. Said laser travels on a path specified by the arrows before being reflected upward by the mirror shown onto the AFM tip, which sits on the end of a cantilever which can be seen with the naked eye. The AFM tip is slowly passed back and forth over a surface at around the 10 nanometer range, which produces a topographical curve on which features can be identified. Continuous back and forth oscillation of the tip as it slowly proceeds across the surface produces a topographical image of your object, which is in this case a nanowire.
This is essentially how the Atkin Lab uses the microscope to develop images and data about various substances. These substances range across many applications, from the data obtained about nanowires to the semiconductor materials they analyze.
The research conducted in Atkin Lab on their current project has been dedicated toward the analysis and verification of nanometer-scale wiring that is grown by the neighboring Cahoon Lab.
They are able to verify the qualitative consistency of these nanowires using SNOM. They can obtain information about various properties, like the electrical conductivity in different parts of the nanowire. Atkin Lab also has various other simultaneous projects, primarily focusing on material analysis in the realm of physical chemistry.
One project they engaged in has been to use vibrational feedback from NSOB technology to characterize patterns of DNA, which relates directly to DNA sequencing. Another has been to develop surfaces for protein analysis using gold and mica flakes in order to analyze proteins without denaturing those in contact with the light.
There's also a lot of potential in every single discipline that overlaps with chemistry: astrophysics, quantum mechanics, sustainable energy, environmental engineering, and more.
Now we are going to solve a problem that directly relates some of the concepts that we've learned in general chemistry with the concepts involved in the Atkin research. The problem we have chosen to create uses the concepts that we learned at the beginning of the semester, where we studied light, except now we're going to connect it to the diffraction limit. Take a second to look over the different aspects of this problem. So what I've written up here is all the important information from the problem given. This is the power of the beam, which is 6 kilowatts, the duration of the beam, which is 50 seconds, and the number of photons. So given the beam wattage, we need to go from there to the energy per photon. To do that, we start with the beam wattage, which is 6 kilowatts. First, converting that to watts, we get, that's 6,000 watts. And we know that the conversion from watts to joules is that 1 watt is equal to 1 joule per second. So given that, we know that we have 6,000 joules per second. From 6,000 joules per second, we get multiplied by the duration of the beam, we know, which is 50 seconds. We have 3.3 times 10 to the 5th joules. So we know how much energy is in the total beam, and that's 3 times 10 to the 5th. And we also know the number of photons. So dividing the total energy of the beam by the number of photons, we can get the energy per photon, and that comes out to 4.15 times 10 to the negative 13th joules per photon. So for part B, we were instructed to calculate the diffraction limit of the light wave, and given the answer from part A, which is the energy per photon, we can go from energy to the wavelength of the light of the photon. So we have the energy, which is 4.15 times 10 to the negative 13th joules per photon. And we also have the constants, Planck's constant and the speed of light. Now, after rearranging this equation, we can see that the wavelength is equal to Planck's constant times the speed of light over the energy, which, plugging in these values, comes out to be 4.82 times 10 to the negative 13th meters. Converting this to nanometers would be 4.82 times 10 to the negative 4th nanometers. So this is the wavelength of light of the photon. But we need to convert this from the wavelength to the diffraction limit. Now we know from the problem that the diffraction limit is equal to about half the wavelength. So dividing this number, the wavelength, by 2, we get 2.41 times 10 to the negative 4th nanometers. And that's the answer. Thank you guys for watching this video. Let Will and I know if you have any questions left, and make sure to get involved with research at UNC.